ladies and gentlemen, hello and welcome back once again to the webcast series called The Web Report here at the Bloor Group with our partners. We'll hear about those in a second. My name is Eric Cavanaugh. I will be your host for today's event, our Database Roundtable. This is part of the Fit for Purpose, the new Database Revolution web report that we're doing. As many of you know, web reports here at our organization can constitute a number of different elements that combine to create the kind of content we hope will provide you with useful information. So we did an exploratory webcast a few weeks ago. This is our first of two roundtable discussions in which we're going to have a couple experts helping us understand what's going on in the world of database. Then we'll have a findings webcast as well. That's going to be in late April, and we'll have a survey launching fairly soon. We hope you'll take a couple minutes to look at all of that. So let's go ahead and dive right in here. Here is a slide about yours truly and enough about me. So again, the web report, it's an open research process, basically. We are big fans of transparency. So what we want to do is open up the research process to get input from folks like you out there in the real world, because you can help us keep our finger on the pulse of what is happening. So please send in any questions you may have, any comments that you have. Watch out for background noise out there, folks. Send in your comments at any time. We do tweet with a hashtag of BriefR. I'm sorry, with a hashtag of DBRev. It says BriefR on there. We'll monitor both streams during this event. But this is going to be led up by our friend Mark Madsen of Third Nature. He is the chief analyst on this project, working, of course, closely with Robin Bloor, our very own Robin Bloor. And we're talking all about the database revolution. So what is going on here? And folks, I have to tell you, this is one of the most significant times in my history of following this industry, because things are changing, and they are changing at a fundamental level. We just did a show yesterday with a company called DataStax. They're one of many NoSQL vendors out there. Of course, NoSQL stands for not only SQL, and SQL, of course, refers to the structured query language, which has been the de facto standard for accessing information from databases for years. And standards are good things. Standards are very useful because they help basically spur competition and innovation. But what we're seeing now is this whole move to get away from the old constraints. So we have things like massive parallel processing. We have things like in-memory technology. And we just have this whole new schema-optional type world of database solutions that kind of grew up in the world of the Internet. Things like Apache, for example, the Apache Cassandra project, which is a database project. There's also MongoDB. There's just a whole slew of these new databases out there, and there's a lot of stuff going on. So what's the upshot for you out there in the real world is that things can be done very differently these days than they were just a few years ago. You have a lot of different options open to you. And one of the more interesting things that I've noticed is that we've kind of realized in the last year or so, at least I have, that many of the problems that we deal with in the world of information management stem from the fact that we've tried to reverse engineer reality into a relational database model. And that's a pretty complex thing to do. So lots of data quality issues, a lot of ETL gone wild, as I refer to it a lot of times, causes some data quality issues down the road for obvious reasons, because you're moving data, and a lot of that data gets moved because of the constraints built into the relational model as it has existed hitherto. So the fact that this is all changing is really a big deal for all of you out there. There are different options you can have, and one of the stats I heard just yesterday, in fact, is that a major analyst firm predicts that 25% of relational database management systems will be unplugged within the next 5 years. And obviously what's happening there is people are trying to get away from these extremely expensive database options from, let's face it, the big guys, Oracle, IBM, to a lesser degree, Microsoft. And of course, there are some other major vendors out there that have closed source solutions. And let's face it, they are expensive. So some of these new opportunities out there are certainly worth a look, but we'll get into that with all of our experts today. So our first analyst of the day is going to be Rajeev Rawat. I've known Rajeev for a very long time. He's one of the most knowledgeable database experts I've encountered in my day. And Rajeev, I'm going to try to make you the presenter here. If you have any trouble with this, I can push your slides for you. But if you would, just go ahead and click on that slide, anywhere on that slide, and push the down arrow, and let's see if the slides work for you. There you go.
Thank you, Eric. You were exactly right in saying that we are in a revolutionary time when it comes to database revolution. In the next 5 years, we will see the most incredible and exciting environment in what I am calling information acrobatics. So if you haven't heard that word or that phrase coined, this is the moment to remember. The data explosion that we're seeing is across the board. It is in variety, volume, and velocity. Let me give you a sense for that. 1,820 terabytes of data get created in a second, in a minute. 668 million emails are sent in a minute. 695,000 Facebook status updates take place in 60 seconds. 11 million instant messages go out in 60 seconds. 700,000 Google searches take place in a minute. 600 YouTube videos or 25 hours of content gets posted in 1 minute. You get a sense for the kind of explosion that has never existed before. There was never the software, never the commodity hardware that allowed low-cost, high-efficiency computing to do the kind of explosive information acrobatics. Again, explosive information acrobatics. This has never happened before. What you saw happen was what's shown in the diagram here. What I'm trying to show is there was tremendous skill, tremendous capability, tremendous power, but in silos. It didn't connect. On the right-hand side and the red side of the graphic, you see it's free. People are free. They're exuberant. There's excitement. There's movement. And that's the world that we're moving in. In the next 5 years, we will see more and more of that. Let me give you a sense for how this could change the world. First, we could have radical transparency. You could test. So in the sense of radical transparency, there is no tolerance today in the world for opaque transactions where people don't know what's happening behind the box. We're moving in that direction. And the movement of the database revolution will allow us to get more transparency and see what's happening behind the black box. Second, you'll be able to see and experiment and simulate the test results for your business conditions. How cool is that? We've never been able to do that before in the kind of cost and efficiencies. Simulations happen, they're expensive, but we're moving in the direction in database revolution that will allow you to do a lot more of what if. What if you could customize on the fly? So if a customer is making a decision on insurance, you could offer them what they're looking for in real time. Or a tailor's shop allows you to change the fabric to measurements to use. Or an HR organization on the fly be able to test an application based on the requirements change and the qualifications of the applicant. What if data, big data, could allow you to manage costs in such a way that fewer managers, fewer people are required in your business, reducing your costs? The fundamental model of business is changing. Where people used to be experts being run by business managers, they're now experts running the business and finding people to run portions of the business for business management. But in smaller companies, you're starting to see engineers and experts take the role of designing and building their business. So I took a little bit of time, but it was important to share that the revolution that's at hand has never happened before. Software revolution, open source, cost of commodity hardware, all of these have combined. New items have come up, new kinds of data have come up that will change the way that we look at business going forward. So what you see today, I'm really, really excited. What you see today is that many, many, many small companies have taken off. They're off, the checkered flag is out, and they're off and running and chasing. There's new venture capital coming in. There's new functionality that I'll speak about in a minute. There are new skills requirements and new ventures being formed. There's innovation in code. There's innovation in business models. There's lots and lots of great opportunity. Let me spend a minute here to share with you there are at least 4 different kinds of open source NoSQL databases that are coming in that will work with and in extension to the database solutions that we have today. You'll find key value stores that were kind of pioneered by Amazon through a paper in 2007. There is column-oriented open source NoSQL databases, Cassandra by Facebook, Apache Foundation's HBase, Google's Bigtable. So a variety of new software will come. The names behind them are phenomenal. They're not made for business, for commercial business. They're made because they solve a business problem. Solve a business problem that's different than the way business was done before. Things were made for commercialization. The chain is reversed here. That is, people are building for functionality, and it's easy business. So there's a fundamental change in the way things get done. Okay. So you look at this graphic, and it tells the story. The reports of the death of RDBMS are highly exaggerated. Reality is that the relational database management systems still offer and will continue to offer strengths, and it'll take a while for the new, young, agile, innovative, and creative organizations to match that capability. One of the major differences is the robustness of legacy databases. You might have heard the term ACID, meaning atomicity. That is, when you update a record, everything gets updated or nothing gets updated. Consistency, that is, no part of the record is allowed to break the rules of the database. So if something's not complete, it's not going to go. It's not going to update your database. In isolation, applications can run. Each application can run independently and can run concurrently with our other applications. And durability, the information just doesn't disappear. So the core of the relational database systems is that it is 40 years of technology, but it's 40 years of learning, 40 years of skill, 40 years of structure, 40 years of governance, tools to get data in, to get data out, to represent it in a certain way. There's a whole ecosystem. There is a reason why the world exists around relational databases. There are policies to control it, and there's documentation to support it. So even though I was very excited, and I'm still very excited about the new direction that we're going in based on these new databases, reality is more than likely we will need to coexist in many environments, at least in the large enterprises. So what are some of the things that will happen on the NoSQL side? The system's being tested, it's being validated, it's being calibrated. They're going to have the industry as a whole. You, as a participant in the industry, can participate in coexistence, transition, and NoSQL-only strategies. The core, the Achilles heel for large organizations has been data quality and data governance. There are still issues 30 years after the whole conversation started. Only 5 to 10% of the organizations really run an integrated enterprise where they can take advantage of or even try to go towards one version or a single version of the truth. Reality is it's very hard to do, and very few organizations are actually doing it. So when you go forward, you'll be looking at integration of new technologies and old technologies to marry them together to run the organization better. Okay. So we're off to the races. We're not at the finish line. At the start of the race, everybody looks fantastic, which is what the industry is looking like now. At the end of the race, you'll see the pictures at the bottom. That is, fenders will have fallen off. Things will have become really hardened. Only a few will survive. It's a fantastic opportunity for growth. Gaps you can close. These are specific areas, whether you look in technology, you look at strategy, you look at the enterprise, you look at vendor environments or innovative ventures, whether it's just growth of the business, there is opportunity all around. It is time to embrace it and to promote the direction that we can go in. So with that, I would like to hand this conversation back to Eric.
Okay, that sounds good. And let me go ahead and make Robin the presenter, because you are up next, Robin. And you should be able to push the slides now. Just click anywhere inside and use the arrow to go down.
Okay, we'll try this out. Yeah, it worked. Okay. Well, Rajeev has, let's say, introduced the scenario that we've come into. What I wanted to do is just talk through a few issues, very pinpoint issues in actual fact. The first is really what happened. What I've got here is a slide. If you look at it, it's actually fairly complicated if you look at it. But what I've done is I've divided applications into various categories. If you look at the vertical axis here, we've got roughly response time. It's logarithmic, by the way, so that actually is much, much taller than you would think it was, for those that understand logarithmic scale. And I've just done what you would call a kind of rule of thumb horizontal axis, which is workload size and complexity. And if we look at this, then what we've got is a set of waves. So you can see the number 1960. In 1960, we couldn't really do anything in an interactive manner. Everything ran in batch. Even batch wasn't particularly fast. Go forward 10 years, and you're still in a batch world of the 1970s. We didn't really embrace the transactional world until we got around about the 1980s, at which point in time everybody had these green screens and were keying in transactions. So at that point in time, we take in a transactional world. We begin to take it in. But, you know, there's a kind of limit on what we could do. Go forward 10 years. And we're much, you know, we can do much, much more with transactions, and we're starting to get towards interactive applications rather than just keying things in, go forward another 10 years. And, you know, we've pretty much got transactional under wraps. Interactive is getting much more sophisticated. We're entering the era of real time. And in the past 10 years, we've gone to extraordinarily fast real time, right at the bottom end of the scale. But this is how the industry kind of evolves. And if you look at these white arrows, these white arrows indicate the direction of application migration. As these waves come forward, slow batch applications become medium in terms of speed, and then become fast, and then it becomes possible to have them working in a kind of transactional way, and then even in a truly interactive way, and then possibly in a real-time way. So as computer power increases and time goes by, we get this kind of picture. So if I go forward one, this is kind of the area, and it's a huge area when you think about it. This is a kind of area that our DBMS was really happy to deal with. You know, and I'm talking not about the relational model so much. I'm talking about what we would call now traditional relational databases. You know, like Oracle, like DB2, like SQL Server, and so on. But once we got to this point, those old engines couldn't give us what we needed. So if we had, you know, really large amounts of data, they blew out. And if we had genuine real-time interaction, then, you know, we needed specialist databases, you know, like databases based on time series, the streaming databases, and so on. And the first thing that happens when we get into a new wave as to what is going on is that you get point products appear. And I would personally describe the NoSQL databases as point products in the sense that they have been built with a very specific target in mind. They will, or we can debate about whether they will broaden out to become general purpose products and to be able to target a much broader range of applications, but at this point in time, they are point products. But what is not, in my opinion, a point product anymore is the column store databases that have actually extended. I mean, if I was to draw, but I didn't, if I was to draw a column store area, it would go beyond where the relational area is. So that's just one perspective. This is what's going on, and part of what's going on is what we're seeing an emergence of new database products, some of them based on a relational model, some of them violating the relational model, and they've come into existence simply because of the march of technology. So I wanted to mention the SQL barrier. It's kind of an interesting thing in the sense that if you've got small amounts of data and you mess about with it on your desktop, in anything, well, in the things like ClickView that you can do, or in Tableau that you can do this kind of thing, you get a pretty immediate response, and you can mess about with the data to your heart's content. But if you've got a big database on the back, then SQL becomes a barrier unto itself. And this has been a problem with databases, with relational databases for a long time, in the sense that, yes, you could write stored procedures, put analytics in the database, but it didn't give you the interactive capability. You stopped at a kind of batch capability, because as soon as you threw SQL at it, even if after you'd thrown SQL at it, you were invoking various kinds of statistical algorithms to analyze the data, when you got your results set back, you couldn't start joining that data to the data in the back-end database. So there's this kind of SQL barrier. And that's, you will find that there's the odd database, 1010 Data is one of these databases, that actually is built very simply to get around this problem, so you can behave as though a big heap of data was kind of like a spreadsheet. The other point that I wanted to raise is simply that MapReduce thing. I mean, really, what's going on with MapReduce? And MapReduce was invented, I suppose. I don't know whether the term was invented, but the use of the algorithm was put into practice by Google originally for searching the web. And the thing about MapReduce is that it's an algorithm that automatically allows you to create scale-out parallelism. And that pretty much is the point. You know, at this point in time, there's an awful lot of people that are coding in MapReduce, and I can imagine them getting serious headaches coding in MapReduce, because you're kind of coding to a kind of structure that most people aren't used to coding for, and you're now trying to think in terms of parallelism. But in actual fact, what this diagram is pointing out really is that there are two forms of parallelism. One is pure scale out, which is where you just partition the data between a whole set of resources. I mean, it's represented here as CPUs, but it's resources. And you process each part of the resource, and then you bring it together. But there is also process partition, where you break a process down serially, and you pass it through resource after resource after resource. And MapReduce, and I'm just kind of pointing this out, not particularly carping about it, but MapReduce is really quite good at data partitioning. In fact, it's built for it, but it doesn't do process partitioning very well. It does. I mean, you've got a reduce phase, and you can do map and reduce, but it isn't structured for process partitioning. And I mean, and the reason for saying that is simply a fair amount of what's going on right now in terms of scale-out architectures is based upon MapReduce, simply because everybody is adopting it. Everybody's trying to, well, not everybody, but a lot of people are adopting it and trying to do stuff with Hadoop and so on. So that's the MapReduce thing, and that has also changed the game, because what we have now is an acknowledgement that databases should be architected to run in terms of scale-out parallelism. And the relational databases, what I call the traditional relational databases, basically they weren't. Okay, I can pass it back to you now, Eric.
Okay, I'm going to go ahead and, there you go. There's Malcolm's slide. So, Malcolm, you're up next, and I can push your slides for you. So just let me know when to push them, but I'll put up your, it's actually your second slide, big data is used differently.
Thank you, Eric. Following on from what Robin was talking about, to me, I think the revolution we've seen is when I started in this industry, the focus was on process automation, and today data is king. You know, in the good old days, data, if it was thought of at all, was a byproduct of automation and not very exciting. And we've gradually come to a realization today that data is an incredibly valuable resource, and we need to get as much value out of it as possible. And now we are able to process vast amounts of data in the new technologies, and we're looking at this paradigm big data, which I think today is at the petabyte scale. Maybe that will change. These actual absolute numbers seem to get bigger and bigger every year. I'm calling it on this slide ultra large scale. And really the technology, or the set of technologies, because it's hardware, operating system, file management system, and database, comes out of the cloud environment in generally. So in the relational paradigm, we see set-at-a-time processing, really looking at populations of identical things. Event data predominates, exception reporting for single things and events, still top-down, and heavy data entry is supported. In ultra-large scale, in big data, we are trying to very often uncover individual facts, say about particular customers, what their propensities are. There's a good deal of master data. There is event data in there, but it's not of the repetitive transaction type very often. And we can aggregate from individual facts, but bottom up, or that surf and drill is supported, and there's some data entry. I would also point out that in terms of the database technology, there was a time before relational when we had different types of database, hierarchical like IMS, network like IDMS, and inverted index, which resembles columnar like Adabas. However, since the relationals come in, most people have been attuned to it, and it does do a lot of work for you. Can we have the next slide, please? So looking at the next slide, in terms of thinking about how the ultra-large scale databases work, one of the typical or sort of the typical environment for analysis today often involves multiple kinds of sources, emails, documents, etc., often referred to as unstructured or semi-structured, as well as some structured data. And there has to be a form of ingestion that occurs to get this loaded into your data space. And I should also point out one thing about ultra-large scale data, big data, is that at least on the projects I've worked on, it's impossible to back up that data space. It's just too big. It's often the equivalent of what's in a container. Now, ingestion is a difficult area. It has to be tackled if you want to go into big data analytics. If we look at the relational world, as I was saying a moment ago, there's a lot of things that are done for you. One of them is that you're able to load data in quickly through things like SQL Loader or bulk copy program. In the big data databases, they're columnar, so essentially every attribute that you're loading, and a lot of this is unstructured, is going to become, as it were, its own individual record, and they'll be spread across a lot of different tables. That can be an Achilles heel. So we have something here that needs to be carefully looked at for anybody working on these kinds of projects. So ingestion can be difficult. It has to be tackled. Also, there's a governance issue here. We can have replication of data across different sources. You will need things like service level agreements or engagement agreements with the different sources. And those two are something a little bit, I think, unfamiliar in the relational world. So we are seeing, as it were, an extension of some of the governance requirements that are in relational as we go into big data. And that, again, is something I think that's going to have to mature as we go down this path. If we can proceed to the next slide, please.
Yep.
So the data space in a big data environment is not going to be a uniform blob of data. The reason is that even to answer specific questions, we have to rearrange the data or reshape the data to get it into that form. And again, if we're ingesting, we may have simply mirrors of the source to start with, and we have to do some form of integration from that data. So MapReduce is now being used as a kind of ETL methodology to move data within the data space. However, as we can see in this diagram, there is an architecture in there. So this, again, is, if it's akin to anything, it's akin to the kind of typical layered architectures we see in BI environments, where you have like a staging area, maybe a reprocess area for errors, then a change data capture layer, and then integration layer. I'm not saying this is actually how it always works, but you get the idea that there's different layers doing different things. So we have it also in the in the columnar database world. However, this does not seem to be yet very mature in thinking about data, in the thoughts around data architecture, how you'd lay this out, how you would orient the overall segmentation of the data space to kind of give you the equivalent of something like an enterprise data warehouse and data marts. Again, I'm not saying we implement that model, but there is some kind of structure in here, and I don't think we're mature enough yet. We have to get to a better understanding of how to use the columnar databases at this higher level. Eventually, you're going to have models on top of these to make sense of it also. So if we can go to the next slide, please. There is no common notation for the columnar designs. Over on the left side, we see a traditional data model leading to a database, a relational database implementation. But over on the right-hand side, I've got a columnar database. I've kind of laid it out in a relational view of it. But where's your data model? Well, there isn't one. And unfortunately, the programmers are creating the metadata to instantiate the actual tables. Furthermore, the rows of the tables in the columnar databases have quite a large composite key, part of which is a column family, which has to be declared prior to the construction of the table, but also contains a column qualifier which can be substituted in at runtime, so you get very variable rows, and it can be that only the programmers understand the structure of the tables because of that. So again, this is a very difficult environment, and the overall lack of a data model, which you do have in the relational world, vis-a-vis the columnar world, is troubling, because we have structure of data storage in the columnar world, and then the actual semantics, that is the relationship of the data in the payload of these records to the business information which we're trying to analyze. So ontologies are very important to have in this space, and being able to match business information as such with the underlying storage model can be quite a challenge. So I think we have to get this area matured as well. So I think there's tremendous opportunities here for a sort of extension of data modeling, but you have to unlearn the relational paradigm. And then if we can go on to the final slide, I think that having data dictionaries to deal with all the components that exist in the ultra-large scale columnar databases is incredibly important. And without this kind of data dictionary, both the developers and the users will get hopelessly lost, because there's a lot of things that the relational world does for you which you're going to have to do for yourself in the columnar world. So all of this is extremely important, and I think that the promise is great in terms of being able to do the analytics, but a lot of additional work is required, as one might expect. I see it maturing in the years ahead, but right now I would say that Achilles' heels exist around ingest, around the lack of models and architecture, and also in the usage of the columnar databases. If you do the equivalent of select star from, it's not going to work real well. It'll grind to a halt. You're going to have to, in your analytics, only deal with selected columns. That's what this stuff is built for. So those are just some thoughts to throw out there, and I'll hand it back to Eric.
Okay, excellent presentation. Really good stuff so far, folks. And now let's hand it over to Mark Madsen. Just click anywhere inside of there, and you should be able to push the slides down, but let me know if it doesn't work.
Okay, thanks, Eric. So that's me. We don't care about me. So I'm just going to follow on to some of the same things that people said, and I'm kind of in the exact same mindset that Malcolm is, so I won't try to replace any of what Malcolm said, but I would say that the future of data is the database, and the real question that comes up then is what we mean by database. You know, we talk about databases today implying that they are all relational, and as you heard before by a number of people, before there were relational databases, there were pre-relational databases. Specifically, the things that really caught on and were usable were IMS and there's a hierarchical database, and of course network databases, you know, Codicil, IDMS, things which were network-oriented databases, which is kind of how an object store or some of these other things really work. When you look back at that history, there were some things that these databases assumed that we don't really assume in the new form of databases, one of them being ACID compliance and the other being schema. When you really think about, say, these early databases, even though they were hierarchical or network-oriented, these databases assumed a global static schema model, and they assumed a limited set of typing and type constraints, and they assumed ACID compliance. And those things are relaxed in a lot of these parallel or modern NoSQL databases. And what's interesting about that is that it does make them somewhat different from what you would be expecting out of one of these older databases. The simple relaxation of a schema model, as Malka was demonstrating with a sparse row store or sparse column family, where you have not just null values, which would be an obvious way to model that in a traditional relational database. The column itself, say the measurement for an event, simply doesn't exist. And that's a different statement than saying I don't know what the value is, or, you know, a lack of measurement versus a lack of existence of a measurement. And it's a nuanced but important aspect of things. The types that we're familiar with dealing with in a database are fairly low. We have problems, too, with a fit with network parallel computing, which is what Robin was referring to earlier when he talked about data parallel versus process parallel. When you have to chunk up data and distribute it across a bunch of nodes, you're basically talking about some form of shared nothing parallelism where each instance, each component is running on a node with no direct, easy communication to other nodes except across an interconnect, which is what parallel databases do. In order to do this in a MapReduce environment, of course, you redistribute the data. You basically reduce and then map. And so you have a disconnect between scalability and execution of databases out there in what we would call, you know, a cloud environment. And then I won't belabor the point about the limited API and atomic SQL statements. Basically a SQL statement lives in and of itself, and so it's very difficult to do set-wise refinement and things of that nature. And that creates some challenges for programmers. A big problem with SQL and sets is that when you're dealing with more than one table, but in a program you have an object which is composed of data which is distributed across a number of tables, of course you have to write a SQL query, and most programmers, Java developers, Python programmers, whatever it might be, were never taught in school the proper way to interface a program code to a relational model. And that lack of education is a problem which has been perpetuated by the development software that they have to use, such that it becomes increasingly difficult as a programmer to talk to a database. And that isolation of code and code data structures from database and abstracted data structures creates a real problem. And the tooling, if you're trying to use Eclipse and you tried to use, say, embedded SQL in Java, God help you. It just basically kills your syntax checking, it kills automatic builds, it kills 100 other things that are useful in the development environment. So a big onus or burden has been left on the developer to do things by the development tools vendors and the database vendors, who are equally implicit in ignoring these challenges. And when they talk about things in this world, we talk about databases as if they're all the same. Well, if databases are all the same, just looking at the relational world, why are there so freaking many of these things? And then you get off into the column family stores, hierarchical stores, network stores, object stores. These things are all solving specific, unique problems for different purposes. Some of them are my exact same workload, only scaling up the volume. Some of them are allowing me to go to extreme levels of scalability in a shared nothing model, keeping the relational intact. Others relax some of the ACID constraints but keep relational. Some of them jettison relational entirely and go a different direction. And they're done for specific purposes and workloads. And the trick is to know which workload applies for which technology, something which is an even more rarefied skill, because what you usually see is the future of data being positioned as the NoSQL side. And I'm going to lump Hadoop / MapReduce and things like that for the analytic crunching, not just the application building in that NoSQL, despite the fact that when you look at the NoSQL moniker, the bulk of that market is targeted at application development support, which might be query light but probably not query intensive applications. And what they're dealing with is this new sets of data, transaction logs, event streams, documents, objects, things like that, which create the hell on earth in the relational model, which is why it gets jettisoned and why these things are very popular. But over time, as we've seen with other aspects of data, things came up that worked. And one of the longevity pieces of the relational model is simply that it allows you to relate data. And you usually, when you're a programmer building an application dealing with a couple of objects, an object store works great. It's when the second programmer working on a different system comes along and needs to be able to work with that data that the NoSQL world becomes hell on earth. A friend of mine just recently related a problem where a NoSQL database was used for an application, and then it was discovered after the fact that they needed to go after that data in a slightly different way. And in many of the NoSQL stores, much like hierarchical data stores of the 70s, you have single access paths. You can navigate the hierarchy top down, but if you need to relate two disparate hierarchies, two distinct objects, and there wasn't an index built on an attribute that is shared between those objects, you have to remap your database. You have to build over the entire database a separate index. You have to build something into the implicit schema that's there, because there isn't a global static explicit schema, nor is there a global dynamic explicit schema. You have to go through some real hoops. And so the data modeling aspects in the NoSQL world, when you go beyond one application, one set of objects can become enormously complicated and very difficult to manage, which is why you're back to this fit-for-purpose world where you have to very carefully isolate the workload, the application, the things you're doing, and then think about the application-specific nature of databases for the purpose that they're for the workload that they're good at, and figure out where relational shines, where NoSQL shines, where other things shine, and you probably end up exactly where Malcolm's architecture slide showed things, which is a big picture of raw data, of base data, which has been somehow fitted into something where it's metadata discoverable through tools, whether that's automated metadata extraction a la text and term indexing in docs, or metadata and structural inferencing using interesting algorithms over tabular data sets where we don't actually know a lot about them until we assess them, figure out the value domains, figure out the typing, figure out what's there or not, whether there are nulls or not, and whether there is a statistical linkage based on the content and the naming of the data to data that's stored somewhere else, so that you can infer a relation, so that you can once again get back to what the relational model gives you, which is queryability. Relational model isn't all about SQL, and it isn't all about static global schemas. It's about the relatability of data. And so we're looking at things where technologies fundamentally are not perfect replacements. You don't slap in HBase to replace Oracle. You don't slap in Oracle to replace Cassandra. It's a world where you have to look at the trade-offs between these things, because each technology, and not only technology but implementation of that technology, is a trade-off. So there is a trade-off between relational and hierarchical and network. There is a trade-off between not processing as you store and putting it into HDFS as a file system versus processing and ingesting that data, which is a subtle but key point that Malcolm made too. The ingestion process should capture some level of metadata, even if there is no global schema, so that you have some utility. But the lack of those things today means there's some significant trade-offs in what you do where. And if you don't think about the total workload and just think about a single point use or abstracted use, which is the advice you're being given today for Hadoop, find the $1 million problem, great, you found the $1 million problem, now what? And I think those are the questions for the future. And so with that, I'm going to turn it back over for some dissection and discussion to Eric to moderate.
Okay, guys, we have a lot of good questions in here already. And first of all, kudos for all those good presentations. I think you all took a slightly different angle but hit on a lot of really key points. So, Robin, I guess I'll bring you back in here to answer a couple of these questions, and then Malcolm, Rajeev, and Mark, feel free to comment as well. One of the attendees wants to know about semantics, and I think Malcolm did a good job with his data dictionary of referencing all of that. But, Robin, what do you think about the role of semantic disciplines in the sort of big data picture?
Well, my first impression is that they aren't anywhere right now unless somebody's got something to show me. I've always had the opinion that, the schema within a database, or the schema as we normally understand it, the catalog in a relational database is what always comes to my mind, is semantically poor. In the sense that it only describes a structure, it has no dynamic capability for redefinition, and so on and so forth. I mean, I could reel off a whole bunch of things. In the newer databases, the situation is even worse, because people are not, at this point in time, and again, someone can correct me on it, but at this point in time, people aren't really trying to do MDM, which is going to need really good semantics to be done well. Around any of these very large databases. These very large databases are pointed at very, very specific problems, and the integration will come after, if it comes at all.
Yeah, right. And Mark, I'll throw this one out over to you, because you were talking about Hadoop a little bit. One of the attendees has a good question. Is the term MapReduce limited only to Hadoop, or can it be used in other contexts?
I think that's a great question, because the way the market has been presenting things, they are interchangeable. And MapReduce is a parallel programming technique, and if you use the specific Apache code, a processing environment, and that is how Hadoop does its work. But Hadoop itself also comprises a storage mechanism, which to me is one of the interesting aspects of it. It is both storage and processing in one ball, unlike having two balls, one for storage and one for processing. But there are other things which implement similar models, and then there are ones which extend beyond simple data parallel processing, whether it's LexisNexis with HPCC, which is an open source implementation for parallel data processing, parallel programming languages like Scala, which you just program in parallel across your data structures but doesn't include persistence, or something like, what was the other one that just came and went? Sorry, there's another one. Oh, Pervasive Data Rush, which is yet another parallel programming environment, and which can actually run on top of HDFS but jettisons the whole Hadoop thing or lives as the executor underneath. So there's a lot of ways to get there without having to use specifically Hadoop or a Hadoop distro, although that is the gorilla of the market at the moment.
Right, and I love this term. I think it's referred to it as eventual consistency. So Rajeev in his opening slides referenced ACID, and of course that is part of what ACID is all about, the basic fundamental rules of database technology. And some of these new database systems were designed to avoid that particular constraint. In fact, I think all of these new systems were designed to avoid one of the old constraints. And with that, I just wanted to kind of mention this concept about a data dictionary. And Malcolm, you had that in your slide. One of the attendees asks or mentions having a data dictionary is nice, but how much of its usage can be automated? Still, the burden seems to be on the end user. And I guess my thinking is it seems as though in a very well-architected information environment, you could have some kind of a real-time data dictionary just trolling around in your system, and obviously you don't want it to shut things down necessarily, but at least throw up flags and recommendations and things on a fairly regular basis. But is that still a bit pie in the sky, as well as this concept of a sort of automated data dictionary that sits over your information architecture, Malcolm?
Well, I think there's a number of things. First of all, it's difficult to automate the structure of the sources. You have to have them described. It can be to some extent extracted from the schemas or database catalogs of the sources. So maybe there's some scope there. On the other side of it, though, right at the far end of the analytics, you have got to have semantics. You're trying to see this data through a lens, which is going to be some kind of ontology, some kind of model of business reality that you want to see the data shaped into. That has to be specified by the ultimate business, the guys doing analysis in this space, and that has to be incorporated. And then in the middle, you've got really the description of the segmentation of the data space, like the equivalent of schemas. Really sitting out there, and how you're shaping the data as you put it into this environment, which to me is a bit like an oil refinery. You're shoving raw data in one end and distilling it into valuable information products as you go through it. So you've got intermediate processing stores with things like MapReduce, putting them in, and Mark, I think it was alluding to how you have to reshape the data to answer questions. That bit too is not going to be automatable. That has to be proactively designed. And again, having done these projects, there's tremendous value in driving things through data dictionaries, not having them as documentation tools, but to the extent you can, doing forward engineering through them. Again, my worry is that unless you do that, it becomes the sort of hopeless mess we did have in the pre-relational world, where, and I was a programmer on these things in those days, where the programmer, it was all in the individual programmer's heads as to what was going on, and nobody else could really use it. End users certainly couldn't query the database. They had to always go through programmers. So I think, yeah, some automation is possible, but a good deal of it is really not.
Yeah, good point. And Rajeev, I want to bring you in on this next question. You had done a good job of kind of outlining the different kinds of database technology that we have here. I'm just looking for that slide at this moment here. But column stores obviously are one part of that, and one of the attendees wants to know, I know some of the answer here, but maybe you can describe it better than I could. What are some of the key benefits of using a column store database as opposed to a relational database, and is it just in the realm of analytics that it becomes valuable to do so?
Well, scalability, speed, the cost of platform, programming. In every single aspect, you can realize if you apply the right approach to determine what it is you're trying to do, you benefit on all sides. There is, of course, the consideration of what kind of data you've got, what kind of complexity you have, and based on data complexity, you can choose a different option, but along all of those lines, you can have savings as well. When you look at your skill set, that is the other thing in the ecosystem. What do you have installed? And what does your organization allow you to do? Look, there's been a lot of conversation here about the barriers for the unstructured approach of databases. And I think we're missing something. There's a massive, bigger transition happening, which has to do with cloud virtualization, low cost of commodity hardware, and in addition to that, yes, skills are expensive. There's less documentation. Programmers are doing the work, but there are costs involved today in running your data warehouse right or your databases right. So I think all of those things go into consideration on choosing whether you're going to go a traditional system or you're going to go invest in something that is a columnar database such as a Cassandra or an HBase or the Google Bigtable. So the applications can vary.
Yeah, that's a very good point. And Mark, let me bring you in on this one. It's a very interesting observation by an attendee. Do you think that a dynamic schema model is the future of database?
That would be my hope, but I spent last year trying to just understand the theory and what, information theory, and it got really complicated really quickly because it gets down to fundamental questions about what we mean by information or data, and even trying to just get to more codified, simple standards. One of the people I managed to pose that question to was Wolfram from Wolfram Alpha, who, Wolfram Alpha is an amazingly neat system for doing pretty interesting stuff. But their knowledge engineering and data management problem there, I thought for sure they'd have dynamic schemas, and have figured at least the rudiments of that out because of the way you pose questions. But what they actually have is semantic mapping to multiple taxonomies or schemas in different types of physical stores. So you might actually take tabular data and store it in a network store, a regular database, and a file or tree structure or something for different purposes depending on how you wanted to query it, which is a physical layering. Then there's a logical mapping of the same schema to these different stores, which is kind of like a dynamic schema, except that the schema, the attributes, the elements, is still fixed. And then over that, there's a mapping from language, from semantics to the schema in order to be able to know what, facts and measures and so forth are. And the way that this is all constructed is exactly what Malcolm said. It's manual. And so far, there's a lot of forays in different things, but they seem, from my reading so far, and I don't profess to be an expert, mainly around the structural aspects of data and data storage, and far less about how you construct schema, given that in some ways schema is a choice because of abstraction and aggregation, and is a calculated metric, which is x times y plus z, a piece of data or a piece of processing applied to other data for which you therefore shouldn't have the schema. And depending on what you materialize in a database, the answer could be either, which is a way of saying I've got no clue.
Well, that's a very good point. And another attendee has a very good observation, Robin. I'll throw this out to you. The attendee writes, doesn't all of this variety in systems, technologies, vendors, et cetera, make it certain that no one, or that one won't be able to find qualified professionals to run any specific application unless this consolidates? And until it consolidates, you're stuck with who you can find, right?
Super question. Because it's probably true, but it depends upon your product. I mean, some of these products boast low overhead in terms of management of the data, and from what I can see, I haven't used any of them, so it's only a matter of what you can see by kicking the tires. Then the DBA overhead is very low. There's an awful lot of products out there that don't have many tuning capabilities, and the tuning capabilities are very easy to understand. I mean, tuning an Oracle database, for instance, used to be, an art rather than a science. And you would tend to configure really quite large numbers of different tables, and you would tend to care about the links, and you tend to care about the indexes and so on and so forth. You don't get that particular problem with many of the new products, and it certainly is quite clean in terms of column store databases, because normally their physical approach to actually storing data is just to chop it up into columns and to scale it out across multiple spindles, and therefore it doesn't need that much help, and it will or may have a hashing capability, and the hashing capability is pretty much self-managing too. So, in terms of that side, yeah, I don't think that would be too big a problem, but in terms of the programmer side, I foresee massive headaches. I mean, my experience of actually building systems was, in terms of using new products, I used to have to do something badly before I did it well, because until you actually do something, you don't really know the characteristics of what you're dealing with. And therefore, I foresee a lot of bandaged knees with some of these products.
That's interesting. Well, Rajeev, I'm glad you brought up this whole point about cloud and cloud-based database management, essentially. Of course, all of us know about EC2, and you have to think that a lot of this stuff is going to continue to move forward in terms of the functionality offered and so forth. And, I just think of other things like renting analytics, for example, or, just sort of offloading a lot of what you're using your Oracle or IBM DB2 database for today to other systems. And I think this just speaks to a comment that basically anyone out there who is spending a lot of money on database technology should at least take a step back and look at their overall information architecture. What are their business needs? What are they doing? How can they leverage some of these new tools? Because the other nice thing for the users is that there has to be pricing pressure, it seems to me. But Rajeev, what do you think about re-architecting your information systems to leverage a lot of these new technologies?
One of the claims that most of these small startups, and one of the benefits that they are putting out there, is that it addresses some of what Malcolm was saying, much of what Mark was saying, some that Robin is saying, is that a lot of expertise here is going to reside in the programmer's head, and there's not a lot of documentation. Well, I mean, these startups are not, they're building a business. They're investing, they're growing, and VCs are not investing in dreams that don't have the potential of paying off, right? So what are they saying? They're saying, we'll do it in the cloud, and it'll be infrastructure on demand. It'll be service on demand. You tell us what your business needs are, and you focus 75% of your time doing your business. We will do what's required to run and provide you information, contextual, decision-oriented, real-time information that is multi-temperature. Okay, it's faster. You don't have obsolescence issues, and you don't have programming headaches. So I think much of what we're talking about 30, 40 years ago is kind of coming around in a different way, right? Object-oriented databases existed 40 years ago, but it's coming around in a different way. It's a different environment today. We have different tools. And so I think you will see a whole change in the way infrastructure is done. Many small and medium-sized companies could never afford the kind of analytics they can afford today because of cloud, because of virtualization, because of software as a service, infrastructure as a service. And so this is the way, there's a lot of dynamic change, and that's going to happen. The point is, how will we play to modify it, to adapt it, to promote it, and to benefit from it?
Right. And Mark, I'd like to pull you in again. All this talk of the cloud is great stuff, but in our survey of the information-oriented architecture, we found that most big businesses are not seriously exploring cloud, and I have to think that a huge reason for that is just reliability and uptime. For any kind of mission-critical system, you want to make sure that you can put your hands on the problem just as soon as it occurs, because unless you're a huge client of a third-party provider, it's going to be difficult for you to get things back online, and it's just a sort of a fear factor involved in all that. But how big a deal is that in your opinion?
Well, it's both real and an entire fiction made up by companies invested in selling you IT data center infrastructure. On the one hand, there's some real truth to it because there's not a lot of cloud providers and there aren't really any standards. It's like the early days of electricity. What voltage, what frequency, AC, DC, who knows? But as a counterexample, there are companies running their entire business in the cloud. The most interesting thing that came up was, Netflix running a very large chunk of their business directly on Amazon, which, when Amazon had those major outages where they lost basically, an entire data center almost, Netflix stayed up because they designed their applications to run in a cloud environment with no single points of failure, with no failures, and so they were able to keep their applications moving around different parts of Amazon's cloud and different data centers and remain up, even though chunks of the infrastructure were down. And that's a design pattern. It's a particular model of loosely coupled architecture, and I think that's the crux of it. You can't take SAP and slap it up into a cloud environment. I mean, you can, but not in a simple Amazon cloud with rated boxes sitting out there, because the software is designed with a monolithic, tightly coupled architecture, and that is the code legacy we have today, which is every bit as bad and painful as the mainframe code legacy that we had to convert off of a decade or two ago. And I think until applications are built to run in this interesting new environment where some of the old assumptions around coupling, around the reliability of hardware, and around soft failure, until those things are considered, that reliability problem is true, but if the software is designed to run in that environment, the reliability argument is false. So it's kind of an interesting yin-yang problem. But to me, that means 10 years of hard slogging, and then all of a sudden, one day we wake up and things have just been transitioned over in what seems like an overnight fashion, and everybody is talking about the death of IT data centers in a much more realistic fashion.
Mm-hmm. And of course, a lot of these new database technologies were designed specifically to avoid issues like failing, right?
Yeah, well, and that's one of the interesting things about ACID compliance and relaxing the C in ACID compliance in order to have a more resilient and tolerant cloud database. And most databases we look at don't really translate well to a cloud environment because they weren't architected to run, and they make specific under-the-hood assumptions about how they're running that turn out not to be true when everything is virtual.
Right. It really is fascinating, the change. And Malcolm, I'd like to bring you back in here. And we are going a bit long, so any presenters, if you have to drop off, I understand. But we'll go for at least a few more minutes. You know, this whole concept of data in motion really fascinates me. And, of course, the old model, which had all kinds of constraints that it took into consideration, was that you would capture and persist any significant data that you found. But now we have all this big data, or as one CEO of a NoSQL vendor calls it, data exhaust, stuff coming off RFID chips, stuff coming off all kinds of different sensors in power plants, for example, all kinds of data that is just incredibly voluminous. So you don't really need to persist all that stuff anymore, and in fact, you can do things with it while it's still floating around there. How big a change is that in your opinion?
Well, I think that's important, and you're right that, in fact, you want to monitor this stuff because you don't want to sort of store it and do averages over it. You want to see if there's sudden trends appearing, like problems are appearing. You know, if you're getting feeds from logs and click streams and things like that, to actually do something quickly. I mean, you know, if you have, for instance, a website where customers come in for insurance quotes and they abandon their quotes, you've got to call them back pretty quickly if you want to try and figure out why they've abandoned the quote. So, but I'd like to make a couple of other points on top of that. One is that we're talking a lot about the containers here. And with the analytics, the content's also important. You can, yeah, sure, a lot of people can now get access to things like, you know, social media feeds, and they've got the horsepower to process them. But if you're not sort of really up there on natural language processing and understanding the ontology of what of the content of this, you know, massive data, you aren't going to be able to analyze it very effectively. So the semantics and focusing on the content is really important. And very often, you know, in IT, there's a bias to the container. Is the container working okay? And you know, whatever's in the container isn't my problem. I don't think that's true anymore with this you know, new world of analytics, where you actually have to go in and model the data. And I also think that to some extent the skill sets required to do that are they're not that common yet. I have seen some brilliant guys with natural language processing capabilities, but they're rather few and far between.
Yeah, that's a good point. Well, let's kind of wrap up with some concluding thoughts here. And first I'll throw it out to you, Mark, because you made a comment about this. One of the attendees writes, you know, about some of these questions. Have the pioneers like Google and Facebook and Amazon and so forth and Yahoo no interest in standardizing and releasing solutions their developers have found? Hasn't Amazon done some steps in that direction recently? What do you think about that?
I think they have, but you know, they aren't product providers to the rest of us. They're using it for their own businesses, which is maybe a somewhat different beast. And you know, there's still disjoints even in those companies. They still run financial systems and other systems, and much of what they're doing or applying this to is for the purpose of, you know, in the case especially of Google, of delivering services and products. And it just so happens to be useful for some of the analysis that supports those services and products. But, well, I don't know about today, but the last time I checked, they were running a very large Oracle database with MicroStrategy to support a big chunk of their business. So it's not like it's also an either or. There are still these solutions, and that simple fact of multiple different internal analysis systems and data flows tells me that there's probably some interesting bits, but I don't think the hard parts have really been worked out.
Yeah, look, Eric, Malcolm referred a little bit to social media. Right? 2 billion users on the internet, 600 million people sign up every day. 44% of the people who sign up are willing to participate with companies to collaborate and change the brand. 36% of them join not because they like the brand, but they like the product or service. These are very compelling numbers, and this kind of data today cannot be, the volume simply cannot be handled in the databases, in the relational databases that we've got. The costs would be phenomenal. So at this kind of rate, there is no question that the NoSQL databases are here to stay. The question is, how will they evolve, and what role will we play to do that? Amazon's doing a part of their business, and they're running their infrastructure. They're doing it right because it's the legacy data systems, databases, and information management systems have governance and capability to manage precision, and the new systems don't. So it will take time, but we have to wrap our heads around this is going to be something that we'll have to contend with in the future because the volume is so large and it's critical, and it cannot be ignored because it's critical to the growth of the business. Anyway, so I think maybe I've said that too many times, but
that's okay. That's quite all right. And Malcolm, I'd like to kind of bring you in here because, again, to this point of heterogeneity and all of these different database systems out there, I mean, to the average consumer, it was already a bewildering market, and now it's even more so. It kind of reminds me of the Tower of Babel to a certain degree, but there is a common language that can be used to help us navigate through all these systems, and that would be the classic metadata. How big a role can metadata play in helping to onboard some of these NoSQL systems and maintain connection to the old legacy relational systems?
Well, I think it's essential, and I think it can be done. However, I'm also fearful that all we're doing is laying down another stratum of complexity on top of a sort of layer cake of, prior generations of stuff, of architecture, which over time just increases the complexity in large enterprises, becoming, a sort of manageability challenge for enterprises. So the older enterprises really, I think, suffering from the inability to kill complexity. They're just acquiring more of it. It's a massive challenge for enterprise architecture, and it may be something that ultimately inhibits them. Seems a bit, everybody realizes we need the analytical capabilities, but managing all these, prior generations going back to mainframe days is a tremendous challenge, and then accommodating business change on top of that is something I think that we're going to have to face in the future, because I don't think this can go on forever.
Yeah, good point. Well, let's get some closing comments from our very own analyst, Robin Bloor. What's some advice you can give to folks about how to navigate through this new world of database technology?
Well, I wouldn't go in too early unless you've got a really big problem. I mean, I think these are point solutions right now, or very close to point solutions. And there are issues which, Malcolm was just talking about one, you're just adding complexity to the environment. My expectation is the situation is going to get worse as we start seeing the embedded world come online. And, 600 million users sounds a lot, but when you've actually got, a trillion embedded processes out there reporting to you, then the 600 million seems like a lightweight load. So that's going to get worse in one way or another. Metadata is indeed critical. SQL is never going to go away because it satisfies set processing. So it may get augmented. In my opinion, the industry had a really bad time with SQL by leaving it as it was, or by the changes they were bringing to it, not including some of the things it needed to do. And that persists. So, we haven't solved all the problems of the past by any manner of means. But, my kind of advice is, unless you have to do this, I'd watch it until you start to see very genuine success from sites like yours.
Right. Well, folks, thank you so much for all these great questions. Big thank you to all of our speakers today. Big thank you to all the sponsors of our database report. You can find more information about all this at databaserevolution.com. Just hop online to databaserevolution.com. We'll post articles there about the sponsors in particular and also about some other database companies we come across. And we will have a second roundtable on March 14th and then a findings webcast that's going to be in late April. So watch for a survey to come out soon. Please take some time to fill that out whenever you get it via email. And otherwise, thank you so much once again, folks, for your time and attention. We really do appreciate it. And we'll catch up to you next time. Take care, folks. Bye-bye.